All right, everyone, time is up. Let's put our pencils down, and that will be it for our work on passage 7. So the first thing that I'd like to address here is how likely you are to see a passage like this on the actual MCAT exam. And the answer here is very likely. This passage is a great example of a passage that takes organic chemistry principles and concepts and applies them to biological and biochemical contexts. It's these sort of interdisciplinary questions that we've seen in this passage that the MCAT absolutely loves, and so you're going to see tons of these on the actual exam. So it's very important that we actually go through this passage pretty carefully, that we understand everything that we've used to get to our answers. So that being said, let's take a look at what we've actually highlighted here. And in our first paragraph, we've highlighted splicing introns and exons. Splicing being the main idea of this first paragraph, as that's our introduction to splicing in this particular paragraph. And introns and exons as well are pretty good definitions in case we weren't too familiar with these terms to begin with. In paragraph 2, I've highlighted the first two nucleotides are guanine and uracil. The last two nucleotides are adenine and guanine, as these are also sort of main ideas and main themes of this particular paragraph. As this paragraph is essentially talking about structure and sequence of our mRNA strand. And they also give us something that says branch point A, right? And it tells us what branch point A is in this paragraph. And so that may be an unfamiliar term, which it should be an unfamiliar term. And so we went ahead and highlighted this as this is a pretty good definition. In paragraph 3, we've highlighted intron excision begins, as that's the main idea of that paragraph. And I've also highlighted lariat, as that's an excellent example of a definition of another unfamiliar term. In paragraph 4, I've highlighted intron excision concludes, as that gives us an idea of the main idea of that particular paragraph. In paragraph 5, I've highlighted modification of histone proteins, as that's our main idea, and the histone acetyltransferase, HAT, or HAT, which is also relevant to this main idea of this modification of histone proteins. And this is also a good example of an unfamiliar term. And in paragraph 6, we've highlighted study the effects of HAT, as that's sort of our main theme for that paragraph, as it just basically presents on how the effects of how HAT affects protein expression. Excuse me. Okay, so that being said, let's actually take a look at our scratch paper as well. And so, as always, we're going to have a title to our scratch paper, passage 7, questions 1 through 5, and then we're going to give it a pretty identifying title. And I wrote down 2 examples here of things that I could think of. And the first thing that I wrote down was transcriptional modifications, as this could be relevant to this. Also, a really quick giveaway answer here would be just writing down splicing, right? This is definitely very particular to this passage, and it's something that you could definitely read and come back to this passage and understand that you're talking about this passage. Cool. So let's also take a look at the map that I've designed here for us. And so once again, it's so important to write out a map on our scratch paper because this map is basically going to give us directions on our way to the answer, on our path to the answer. Right, so let's take a look at each of our paragraphs here. In paragraph 1, I've just written down intro to splicing. Right, like we mentioned before, splicing is the main idea there, and it just gives us a quick introduction to the concept. Paragraph 2, I've written down structure and sequence, as once again, that's what's going on in that paragraph. In paragraph 3, I've written down intron excision begins. That's the main idea there. Paragraph 4, intron excision ends. That's the main idea there as well. Paragraph 5, other ways to regulate protein expression. And one example of this would be HAT, which I've written down in parentheses. And paragraph 6, I've written down the effects of HAT, as that's going to be what's relevant in that paragraph. So once again, these sort of concise titles for each of our paragraphs, just to give us an idea of what's going on, to give us some way to navigate back to an answer in case we have to, but nothing too time-consuming and too difficult to sort of write out. And then just going through our figures, what I've written down here, figure 1 is our lariate formation. That's the structure given there. In figure 2, I've written down lysine with and without HAT. Those structures are given to you there as well. In figure 3, I've written down the effects of HAT, right? And that's sort of that bar graph in the bottom right of our passage there. All right, so let's take a look at some questions as I move my laptop so gracefully to the left here. All right, and so let's take a look at number 1. And so number 1 says, which of the following best represents the potential sense sequence of an intron? And so, number 1, what we should definitely figure out, right, is what do we mean by sense sequence? And basically, if you should recall, that sense sequence is essentially talking about the DNA strand to an RNA strand. And so, keeping that in mind, what we also notice about all these answer choices is that they all have different sequences. right? The key word here being sequences, because if we go right back to our map, which is not available to the laptop at this point, but we've written down paragraph 2 as being structure and sequence. Okay? And so that gives us immediate directions to go back to paragraph 2 and look at what we've highlighted. And what we highlighted is that the first 2 nucleotides are both guanine and uracil. So, if we know that guanine and uracil are the first 2 nucleotides, that should give us an excellent idea of what we could be eliminating here, right? Because if guanine and uracil are our 2 initial nucleotides in our RNA sequence, our DNA sequence would have guanine and thymine, right? G and T. And so if we're just going through our 4 answer choices, we could immediately eliminate A, B, and D as not having guanine and thymine. And we end up with answer C. Okay? Once again, this question was made so much easier by being able to go back to our map and find out where we were talking about sequences and going back to what we've highlighted. If we didn't have that map, it might have taken us a little bit longer to sort of figure out where that was in the passage if we were able to find it again at all. Let's take a look at number 2. How are intron excision reactions expected to change if all nucleotide sugar hydroxyl groups are synthetically replaced with thiol groups? And so the difference here between a hydroxyl group and a thiol group is essentially one has an oxygen, the hydroxyl group, and the thiol group is a sulfur, right? And so if that's the main difference here, we could also take a look at our particular question and notice that this question is a 2x2 type question. And the way to sort of determine that is that as we're looking through the answer choices, we notice that they all have the similar formats, right? Very similar formats. And basically all of them start off by talking about how nucleophilicity changes, and all of them end how exon elimination changes. And because they all differ on these 2 variables, this is how we end up with a setup for a 2x2 question. And so as I mentioned, this is our setup for the 2x2 question. This is what we should have in our notebooks. And also we should be putting down our scratch paper on the day of the exam. Another important thing to mention about this question is that is this particular question possibly memory implicit or explicit question, right? And so this question isn't something that immediately should come to us from previous knowledge, so it's definitely not a memory question. And it's also not something that we can immediately go back into the passage because it doesn't really talk about changing a hydroxyl group to a thiol group in the passage. And so the only thing that we're left with through process of elimination, I guess, is implicit. But the reason why it's an implicit question is because it's asking us to take what we know before about nucleophilicity, about a thiol, about a hydroxyl group, and about exon elimination here, and apply that to a brand new situation. And so this question in particular is an implicit question. Okay, and then just to point out, I may have missed in the very first question that this would be an explicit question, right? It's talking about basically going right back to the passage and looking for information. And there was no specific answering strategy here other than POE. Okay, so back to our 2x2 question. So as we go from a hydroxyl group to a thiol group, let's first examine the nucleophilicity and how that changes. And so we all should have a good idea that between these 2, sulfur is going to be the better nucleophile, since it's larger and more polarizable. And so nucleophilicity absolutely should increase. And because it should increase, the 2 that we can eliminate immediately are C and D. Okay. The value of this method is that at this point, we are now down to 50% chance of getting a correct answer, right? So even if we have no idea what they're talking about with exon elimination, at least we've gotten 50% of the way there, and we can definitely see ourselves into a better chances of getting the answer correct. But alas, we do know what they're talking about with exon elimination. And so specifically, the difference here is that a better nucleophile is our sulfur. But exon elimination involves basically the kicking off of this hydroxyl or this thiol group, right? So now we have to take a look at which is a better leaving group. And so of the 2, the one that is better at stabilizing a negative charge here would be our sulfur atom. Because of its atomic radius, because it's larger, and because it's more diffuse, this would be our better leaving group. And so if sulfur is a better leaving group than a hydroxyl group, the answer choice that we can immediately eliminate would be choice B. Because exon elimination, therefore, would not decrease. It should increase. So we end up with choice A as being our correct answer. Taking a look at number 3, which of the following best explains the difference in protein expression between samples with and without hat, as exhibited in figure 3. And so if I tilt the laptop just a little bit so we can get a better look at the rest of the board. And so once again, we should notice immediately that this question has the same format going through each answer choice. It's varying based on PKB, whether that's increasing or decreasing, and then it varies based on the affinity of histone proteins for DNA, whether that increases or decreases. And so once again, we could set up our little 2x2 chart here, and so I'd like to write that right above the question here, 2x2. And once again, this is not a question that we can go immediately back to the passage and sort of pick out the answer, and it's also not something that we should know immediately, and so this is going to be an implicit question. Mainly because it's asking us to take previous knowledge and apply it to a brand new situation. Okay, and so the first thing that we could take a look at is the PKB, and I've drawn down here the difference between lysine and our hat lysine. And so if we take a look first at the lysine, we notice that this nitrogen has a lone pair, right? And so the only way that this lysine can act as a base is through that lone pair basically attacking a proton, right? And the same thing exists on hat lysine. With hat lysine, we do still have this lone pair available to us. But there's a huge difference here. This lysine, this lone pair is particular to this nitrogen atom. It can't go anywhere. But this hat lysine is very different in that it actually has a pi bond that is immediately adjacent to the lone pair on a nitrogen. And so we actually could end up with a very possible resonance structure in which the lone pair from the nitrogen drops in to form a carbon-nitrogen double bond, giving us this structure on the right-hand side of the board. Okay, so that's definitely a very important resonance structure, although it may not be necessarily significant because we are increasing charge separation, among other things, but it still exists, right? And so we can still consider this lone pair on nitrogen a bit more delocalized than a lone pair on this lysine. And for that reason, this lone pair on the hat lysine is less available to bond to a hydrogen that is around, and less likely to be basic. And so for that reason, we would expect our PKB to increase. So we can immediately eliminate both choices A and C for having PKB decreasing. And just a quick word on PKB as well. If we weren't too sure of whether or not increasing or decreasing PKB would be relevant to this particular point, or whether it should be increasing or decreasing, something that's very similar that we can think of is pKa, right? If we think of pKa, an acid with a lower pKa than something else is going to be more acidic, right? But basically, something that has a lower pKa than something else is just better at being an acid. And so the same concept can apply to our pKb. But as a lower pKb than another type of base, it's going to be better at being a base. Cool. And so then we're left to take a look at this idea of histone. Okay, so something that we should point out about our affinity for histone proteins to DNA is that the reason why histone proteins have an affinity for DNA is because histone proteins can be positively charged, whereas DNA tends to be negatively charged. So if we look at the difference once again between lysine and hat lysine, our lysine, if it's protonated, can have a full positive charge. So let's actually draw that structure out here. Hat lysine, however, we've mentioned before that it's less likely to be protonated. And so if it's less likely to be protonated, it's not going to have this full positive charge. It may have this partial positive charge because of this resonance structure, but that's completely negligible in comparison to having a full positive charge like this lysine does at physiological pH. And so for that reason, we should expect the affinity for histone proteins to DNA to actually decrease, right? Not to increase. And so we can go ahead and eliminate choice B, and we're left with choice D. Let's continue on. Let's read number 4. Addition of which of the following reagents would be most effective in cleaving the acetyl group of a lysine residue after the addition of HAT? So, once again, let's take a look back at our HAT lysine. So, we may not necessarily be too familiar with anything about HAT lysine. We may never have seen this before in our lives, right? But this particular moiety is something that we should have seen at least tons of times before. If anything, we should have at least seen it in the organic chemistry manual, right? Because I know, just looking at this is a carboxylic acid derivative, right? And which one in particular, right? It's an amide. It's an amide, absolutely. And so what do we know about amides and their reactivity? They're the least reactive out of all the carboxylic acid derivatives. So if they're the least reactive of all the carboxylic acid derivatives, and we know that this carbon is a fairly okay electrophile most of the time, and that's going to be where any type of nucleophilic attack would happen, we would expect our HAT lysine to need an extremely good nucleophile to actually react, to actually make some type of effect. Right, so basically this question comes down to comparing all 4 of the answer choices to whichever would be the best nucleophile in this particular situation. And so if we take a look at our 4 answer choices and just quickly draw out their structures on the board, A is essentially methoxide, right? A negatively charged oxygen with a methyl group. B is this nitrogen that has 2 methyl groups and a negative charge. C is going to be negatively charged bromine, and D is going to be basically acetate, right? Potassium acetate. Okay, so just looking at this first off, right, we could definitely tell that a few of these have much less ability to sort of stabilize a negative charge than do others. And if we go back to one of the key themes about organic chemistry on the exam, we should know that low stability leads to high reactivity, right? So based on that alone, we can definitely eliminate a few of these answer choices. And so, in particular, let's go ahead and eliminate bromine, as that's definitely incorrect. And this carboxylate is definitely also very good at stabilizing that negative charge. Lastly, if we're sort of down between this methoxide and our nitrogen, once again, oxygen should be better at stabilizing the negative charge, and so we can eliminate A and go with B. Additionally, a good thing to sort of realize with this particular question is that all 4 of these, besides this, all 3 of these, A, C, and D, are actually much more reactive when they're attached to the amide, or when they're attached to the carboxylic acid derivative, than the amide is, right? And so that should also be a pretty good indication that these wouldn't be strong enough of a nucleophile to have a reaction. All right, very last question, number 5. Splice factors are proteins that bind to introns and alter the length of intron excised. A particular splice factor binds to the sequence between BPA and the original 3' end of the intron. So I'd like to stop it there and just quickly draw a quick diagram out on the board for us for this particular question. And so if we take a look at our strand, we have our 3' end, our 5' end, and somewhere in the middle we have BPA. And so they're saying the splice factor sort of fits itself in between BPA and the 3' end. All right? And so if it's just sort of sitting there in between BPA and the 3' end, let's continue reading. Upon binding, this protein reassigns the 3' end of the intron to a site that is closer to the 5' end of the intron, but still farther away from the 5' end than BPA. So basically what it's doing is it's taking this particular portion of the strand and just relocating it. Right? So if we redraw this, we could sort of figure this out. Let me try to find a different color here. Okay, and our BPA should still be in the same spot. We just changed the color of the strand that we moved. All right, so basically we're taking that orange strand and we're moving it somewhere else. Okay, and so they're asking us how the binding of the splice factor ultimately affects the length of the protein product. And so going through these answer choices, there's 2 scenarios to sort of understand. Number one, if this orange portion actually does code for something, then absolutely the protein should end up longer, right? If it codes for specific amino acids, excuse me. But there's another thing that could happen, right? This particular orange portion could have a stop codon. And if it does have a stop codon, which it probably may have, what would happen? Right, our protein would end up being shorter, right? So we have two different scenarios that could both be plausible and both are equally likely to happen. So at this point, the only thing that we can determine is that we cannot determine the length of the protein. And so we would eliminate A, B, and C and go with D. All right, everybody, so that was passage 7, and so let's continue on with other practice.